I would like to talk more about domain. So I'm back to page 150. Okay. We did something like 59 already. I'd like to discuss 57. On page 150, and we have function g of x, which is the square root of 2 plus x over 3 minus x. We're asked to determine the domain of this function. And I would like you to tell me what to write. Wonderful. X cannot equal 3. I completely agree. Anything else?
It's all of the solutions.
Careful. Nope. This is a combination of two functions. The function from the top is the square root. The function of the denominator is a linear function. So I have to state restrictions for everything, for every contingency, every possibility that will make me get stuck. One possibility that will make me get stuck is 3, because I can't divide by 0. What is the other possibility that may get me stuck?
It has to be it's even.
Not the square root. Not the radical. What did we say? Did we state here a restriction on the radical? Was this restriction on the radical? Is this a restriction on the radical? No, it's a restriction on the...
What's inside the radical?
Exactly. It's called radicand. So now let's come back. What do I have to write?
2x plus x.
Yes.
Cannot equal -2 minus x.
Say it again. This is exactly what we said. It cannot be negative. So let's go back. What condition did we put on 256 minus x squared? Not less than or equal to 0. I will never be able to apply the square root or the fourth root. If it's even, the quantity under the square root has to be positive or 0. So coming back here, then what do I write? Good. So this is already solved, but this one is not. So it's x greater than or equal to -2. So when I look at the real line or the number line, I don't care for units here. You can. If you want to be super exact, you can. Greater than or equal to -2. This is my -2. This is greater than or equal to -2. But I am told 3 has to be removed. So now I would like someone to give us the domain of this function. That is a combination. It's a rational function combined with a radical. So domain of g, is very good. Very good. Yes, indeed. Very good. Thank you. $62. Any questions from me on 150? F of x equals x squared divided by the square root of 6 minus x. I think we don't need this anymore. The sun is down. Yes. Yes?
X has to be greater than or equal to 0. It has to be, it cannot be equal to 0.
Why?
Because you can't square 0.
0 divided by 6 minus 0 is 0 over the square root of 6, which is 0. Something else cannot be 0, not x. 6 minus x.
It has to be greater than or equal to 0. Greater than or equal to 0.
I cannot rewrite equal now because it's in the denominator.
And equals.
There's just greater than. I cannot write greater than or equal to because it happens that this quantity is in the denominator. So then x is less than 6. And what is the domain of this function then? There is no restriction on the numerator. X squared doesn't have any restrictions. So what do? What is the domain? You have to bring x here and you have to read the inequality from the right. X less than 6. So domain?
Negative 66.
Very good. Okay, moving on. Any questions?
Yeah, why is it negative infinity instead of negative? Is it less
Which
than?
numbers are less than 6?
No, any number is less than that.
Right. Those numbers are less than 6. Any questions? Any questions? Any questions? What I would like to do now, and before we move on to section 2.3, is to list basic functions. We need this for later section. So in 2.2, I would like to look at the list of basic functions. These basic functions are functions coming from different categories that are the simplest possible function in that category. So for example, what do you think would be the simplest square root function? The square root, it's not a function. The square root of 4 is not a function. Exactly, the square root of x. What would be the simplest linear function?
X plus.
Exactly, x, f of x equals x. What will be the simplest possible quadratic function? And so on and so forth. Okay. Before we list those functions, then there are many more, I would like to discuss the types of functions that we will encounter. We may encounter symmetric functions, or we may encounter not symmetric functions. Symmetric functions are of two types. What is called even, an even function, and what is called odd, what is called an odd function. It has nothing to do with the possible index in the function. It has nothing to do, it's just the name of a function. Now, even functions are symmetric with respect to the y-axis. Symmetric with respect to the y-axis. Oops. Odd functions are symmetric with respect to, as abbreviated, with respect to the origin of the Cartesian system, 0, 0. And I would like to analyze both, because when we will list them, I will also ask you if those functions are even or odd. Ready? Here is a function that I know is even. And that is x squared. So the simplest possible quadratic function is symmetric with respect to the y-axis. Now, stay with me, please. Let's say this is x. Can anyone tell us what is this? Right, we know that now. Okay, perfect, perfect. So this must be f of x. Okay, I will continue this line. And you see on the other side, this line crosses the graph at this point. Can anyone guess this value here? Of course, absolutely. Now, I don't want you to look, where is my, I always use my whiteout. I don't want you to look at this side, disregard it for a moment. If this is negative x, I would like you to give me this. No. No. Don't make up stuff. If this is negative x, how much is this?
Talking about the center one?
This point has two coordinates. Has an x coordinate and has a y coordinate. Don't jump. So if this is negative x right here, I would like you to tell me how much is this. Okay, let's go back to the function. We don't remember how to identify, that's okay. So here it is. If I'm asked to plug in blah, I get f of blah. I can change that. I can do anything to it. If I plug in blah, the answer has to be f of blah. That's what I want. You can make stuff up. So then indeed, this here, like this here, this is f of x, but this is f of negative x. Absolutely. Now look at the graph and say, it's very clear that this equals this, and I'm going to write it. What is clear? What equals what? From the graph. F of x equals, don't make stuff up. Indeed. This is the relationship algebraic relationship mandatory for any even function. If the function is even and I replace in the function x by negative x, what do I get back? The original function. Excellent. This is extremely important to understand. Say it again? No. No. We haven't. No. The inverse function is something else. So, here's my question. If I'm given, let's say, x to the fourth minus 3x squared, and I'm asking you, do you think that this function is even? What will you need to determine? To say yay or nay? What will you need to determine? Yes, you're way ahead of me, but what at the beginning, what do I have to find? You're right. I'm not graphing it. Every time I graph, I have to start with the domain because I don't know what to plug in.
The quotient, the differential quotient.
Okay, one more time. We established that for any even function, this relationship has to happen. So now we have a function. And the question is, how will I show whether the function is odd or not odd? Whether the function is even or not even?
Putting the number positive side.
What do I have to determine? What do you think? Exactly. Absolutely. I find f of negative x. And if it equals what? The original function, then what do I conclude? Exactly. So plug it in. Tell me how to plug it in. Exactly, with parentheses. Careful. Minus. That's it. That's it. Okay. So then, please perform the operations. So if you want to come back to your chart, the little table that I created here. So an even function is symmetric with respect to the y-axis, and also f of negative x must equal f of x. So these are the conditions for an even function. I'm going to come back and fill it in. Good. So then how much is negative x to the fourth power? X to the fourth power minus 3. How much is negative x squared? Very good. I'm asking you now, does this equal f of x? What do we conclude about this function then? Therefore, is symmetric with respect to the y-axis or even? Yes. Therefore, f of x is even. Perfect. Now let's talk about the other one. Here's a graph. I know is odd, so I'm picking a function that I know it's odd. Here it is. And that is x cubed. I don't even need to know what function it is. It's an odd function. And I'm asking you a couple of questions now. Here's the first question. I have a point here, and this point has coordinate x. What will be the y coordinate? Thank you. Watch what I do next. For 1 second. I draw a line connecting this point and the origin, and I extend the line, and I obtain a new point right here. For this point, I would like you to give me its x and its y. Of course. And its y. It's y. Don't make stuff up. Don't jump ahead. Say it again. Absolutely. Now, I will ask you to tell me what is the relationship between f of x and f of negative x. What is the relationship between these two? Negative? Not reciprocal, because if this is 5, what should this be? 1/5? No. Negative 5. So then what is the relationship now between f of x and f of negative x? They don't, but there is a relationship. We just talked about it. If this is 5, what should this be? Right, it has to be. So f of negative x in this case must equal. Very good. So this is the relationship for any odd function. It's the opposite of f of f of negative x is the opposite of f of x. So coming back to my little chart, if you want to go back and put it in this case, f of negative x will be negative f of x. Perfect. And now I'm going to give you another example. So let's look at one more example here, and then we'll list those functions. So let's say we have f of x, which is negative 3x cubed minus x. Let's make it plus x. And I'm asking you whether this function is symmetric. Yes. No matter what, if it is even or if it is odd, in both cases, I have to find f of negative x. Mandatory. So that's where my starting point is. So f of negative x will be negative 3 plus negative x. Good. So let's continue here. Negative x to the third cubed. And with minus 3 in front. 3x cubed. And positive negative x. Very good. At this point, I have 3 questions that I'm asking myself. And here they are. 3 questions. Question number 1. Does this equal the original function? If the answer is yes, then I will say the function is yes. Does this equal the opposite of f of x? If the answer is yes, then this would be odd, or none of the above. The answer is yes to only one. There is no function that is odd and even at the same time except the function that nobody cares about, which is y equals 0. So the x-axis is the only function that is symmetric with respect to the origin and symmetric with respect to the y-axis. But who cares about y equals 0 or f of x equals 0? So there is basically no function that is odd and even at the same time. And the answer, yes, it has to be to only 1 or 2 or 3. Yes, because I will determine negative f of x. Determining negative f of x requires multiplying this equation both sides by negative 1, and I can do it. Negative f of x equals 3x cubed minus x. And it happens that these two are the same, meaning f of negative x equals negative f of x. This is a no, this is a no, and this is a yes. Since f of negative x equals negative f of x, the function is odd. Any questions? Is this clear?
We always plug in negative x for x to figure this out.
I'm not plugging in x.
So we always plug in negative x.
Let's take a look. Let's take a look. Look at what we wrote here. If I don't calculate it, how will I know? So in both cases, I have to calculate f of negative x. I have no choice. In this particular case, I also have to calculate negative f of x in order to show that they are equal. But here, I only have to calculate f of negative x. If it happens to be the function itself, then I'd say it's even. So the graph will be symmetric with respect to the y-axis. But if it's not that case, then I have to calculate negative f of x to show that these two are equal. Therefore, the function is odd. If none of the above works, so f of negative x does not equal f of x, and it does not equal negative f of x, then I'll say function not symmetric. Questions? Questions here? Anyone? Shane, you had something?
So essentially, you're just taking the original problem, and once you plug in negative x, if you multiply the original problem by negative 1, it's the same thing as like after you plug in negative x, they're odd, right?
Because the condition requires me to calculate for the odd two things. I have to calculate this and I have to calculate this. I will never calculate this if the answer is yes here. So if I calculate f of negative x and it happens to equal the function, I don't need to do any of this because I know there is no function that is worth anything that will be odd and even at the same time. But since that was not the case here, I realized that the function f of negative x is not the same with the original function. So the answer to this is definitely no. Then I have to calculate the second piece of the odd possibility. I calculate negative f of x multiplying both sides by -1, and then I realize that these two are the same. If these two are the same, then the function is odd. Better?
Yes.
Perfect. Anything else here? Okay, now let's finally list those functions. So the list of basic, which means the easiest, the simplest possible, basic functions from many categories. So linear. You already gave me f of x equals x. And here's the graph of f of x equals x, and you will tell me whether it's odd or even. The simplest possible linear function is f of x equals x, and this is its graph. Odd, even, or none of the above.
You can plug in negative x.
I have the graph. You can do the whole procedure, but I have the graph now. Of course. The function is clearly symmetric with respect to the origin because I had the graph. Yes. Next. Quadratic. But yes, you can calculate it like that. Nothing is wrong with that. Here's the quadratic function. F of x equals x squared, and obviously the function is even. We already worked on it. Very good. We have to remember these functions. So when I say to you quadratic, you have to have this picture in your mind right away. When I say linear, you have to have that in your mind. If I say square root, so f of x equals the square root of x. So this is the square root. Here's the graph, and we have to remember the graph. When we talk about the square root, this has to come to your mind immediately. And here it is. It's not a line. See its domain? See why it's x must be greater than or equal to 0? Perfect. So then, odd, even, or none of the above? Of course, not symmetric. Not symmetric. It's not even, it's not odd. Perfect. Okay, next one. X cubed. We just worked on it a few minutes ago. Here's the graph of x cubed. It's flat here. Do not cross normally. This is a flat. We'll talk about it in chapter 3. And you'll see why this happens. So this is f of x equals x to the third.
Is that called though? Isn't that the name of that?
Yes, it's an inflection point. But we don't talk about it in pre-calc. We talk about it in calculus. But yes, it's an inflection point when it changes concavity from opening downward to opening upward. Good. Symmetric or not?
Awesome.
Of course, we just looked at it a minute ago. Good. Next one, absolute value. Here's the graph of the absolute value. When we say absolute value, this picture has to come to your mind immediately. Bless you. So this is f of x equals the absolute value of x. It's a v function. Okay, so odd, even, or none of the above?
Even.
I can, if your book has this, yeah, let me put it. I don't know if it has it, but let's also look at this, because I would like you to start thinking about this function as well. 1 over x. So this is absolute, so this is cubic. I'm sorry, I didn't write. Cubic, and this is absolute value. And this is rational, of course. So let's look at the graph. We will talk about this function extensively in chapter 3 as well. Here's the graph. Odd, even, or none of the above? Odd indeed. Symmetric with respect to the origin, right? Because I can fold it. Yes. Okay. Yes, they do have the reciprocal function. Oh, okay. And 1 over x squared. Okay, we're going to talk about that. Yeah, I touched up on every type for now. Okay, good. I still have time, yes, about 10 minutes. Good. So let's continue with 2.3. This section is called getting information from the graph of a function. Okay. From a graph of a function. Okay. I would like to copy a graph, and I'll let you choose whichever graph from here you would like to copy, and let's talk about it. For example, I prefer something like this or something like that, but it doesn't matter, you choose. 7, okay. So the graph of 7, although I'm going to graph it, here. It's not going to be exact, and I'm going to read from the book, not from my graph, but I just want to give an idea. Page 169, yes. We are looking at problem 7 on page 169. Okay. Perfect. Here's the graph, approximate graph, of course. Okay. So, getting information from a graph, what would you say about this graph? And then I'll tell you what I would say about it. What would you say? If somebody gives you this graph,
It's piecewise.
say it again.
It's piecewise.
It appears to be a piecewise defined function. I agree with that. Let me be more specific. I think what I'm asking is, for example, trend. So here's what I would say about the trend. I would say this. Between x equals 4 and x equals 0, this function is decreasing. Between x equals -4 and x equals 0, the function is clearly decreasing. Would you agree?
Yes.
Also, I hope you agree that between x equals 2 and x equals 4, the function is also decreasing. Here's how I would write it. F decreasing on the interval -4, 0, union 2, 4. I'm sure you are going to ask, wait a minute, you only wrote parentheses, you did not write brackets. True. The trend does not have anything to do with a particular point. So, for example, at a particular instant, for example, now I'm standing, I'm not moving. Now for the next 10 seconds, my trend is walking. But at a particular point, the function is not increasing or decreasing. So we only keep open intervals for trend. Okay? Good. Now I will also say that the function is increasing on. Notice that I'm not saying from what to what. This is not the point. The trend is not interested. We're not interested when we talk about increasing, decreasing. We're only interested when that happens, not from what to what. You may be tempted to say the function increases from -2 to 4. That's not what I'm interested in. So when I'm asking the question, where is the function increasing or decreasing? You're only giving us when, not from what to what. So you will say the function is increasing from 0 to 2. We're only talking about when, not from what to what. Only when. Also, that's number 2 now. What else I see in this function? I see what it's called, this point. I'm going to call it local min. Local. It also has another name, relative min. So some books use local, some books use relative. What does this mean? So if I can show that there is an open interval near that point where the function values are larger than it, then that is a local minimum. Can I show that? Yes. So right here, around this point, I can show you that there is nothing, no function value lower than this. But in the vicinity of that point, all function values are larger than it. Therefore, this is a local minimum or relative minimum. Since this is, for this function, the smallest possible y value, we will also have to call it, so this is definitely 0, -2. So we also call this point a global or absolute minimum. For this function, there is no other value lower than it anywhere else. Okay, now, question. Is this point a local maximum? No, because I cannot show the open interval left and right.
So is there no local max?
No local max, no local min at the end point of an interval.
Can you explain that again? The one is a local max. I need the local min. That makes a lot of sense.
Because I don't have the open interval. There is nothing here. Endpoints cannot be local. Now, is this point -4, 4? Is it a global max?
Yes.
Yes. The endpoints of an interval can be global, but they cannot be local, because if they are at the endpoint of the interval, I cannot show you the open interval around left and right, around that point. So -4, 4 is indeed a global max, not a local max, because it's at the endpoint of the interval. Is this point anything? It doesn't even exist. Is this point anything? It's at the endpoint of the interval. It could be absolute min or absolute max, but it cannot be either one, because there are other values higher than it, and there are other values lower than it. So this point is nothing. This is the global max, this is nothing, and this is the global min and also local min. Is this a local max?
No.
No, because I cannot show you the open interval, both left and right. Good. So we can read a lot from a function. Now, for this function, I would like you to give me the domain and range. Do I still have time? Yes, 3 minutes. Okay. So I would like you to give me the domain, and I would like you to give me the range for this function. Bracket -4, comma. Cross it with vertical lines and tell me where it hits.
0.
Indeed. It hits everywhere. All vertical lines that you draw will hit the graph of a function in one point only, anywhere between -4 and 4. Perfect. Now about the range. From the lowest y value till the largest y value where horizontal lines cut the graph or cross the graph. -2 to, oh, I'm sorry. So this is 3. I'm sorry.
So there's not 2 global maxes?
At this point doesn't exist.
Oh.
So I'm sorry, it was 3, but I wrote 4 here. You're right. It's 1, 2, 3. I don't know why I wrote 4. Sorry about that. It's right here at 3. Indeed. So the range is -2 to 3. Perfect. Very good. Okay. I do have just 1 minute. Just going to come back here, and I'm going to ask you for this graph on 48, population growth and decline. The graph shows the population P in a small industrial city from 1950 to 2000. The variable x represents the number of years since 1950. Determine the intervals on which the function P is increasing. From 1950 to 19, so I'm adding 1950, I'm adding to 2000, right? 50, I'm sorry, I'm adding actually 25, yes. So 1975. And where is this function decreasing? Between 1975 and 2000. What was the maximum population, and in what year was it attained? Is it a local max? Is it an absolute max? Is it both?
It's both.
It's both. It's the top possible, and I can also show the interval left and right, so it's the absolute and also local. And yes, it appears to be population P in thousands, 50,000 in 1975. Very good. I'll stop here. On what's today? On Monday, I'm going to try to finish this chapter. Hopefully we can. Then the following Wednesday, we're going to review for the test. So tentatively,